thank you everyone for coming. And so today we're going to talk about how we pawn Google Chrome and Microsoft Edge at Pwn2Own Vancouver 2024. So let's knock on Chrome shell by editing the cache and the WebAssembly assemble. So first, quick words about us. We are two security researchers from Palo Alto Networks, and we are working on offensive and defensive research. We are Pwn2Own winners, and we have spoken to many conferences in the past. So in this talk, we'll first introduce Google Chrome exploit chains based on V8 vulnerabilities and how they evolved since the introduction of the V8 Sandbox. Then we'll talk about the bug we used at Pwn2Own and how we actually exploited it. In the third part, we'll talk about the V8 Sandbox and how we escaped it to get render code execution. And then we'll end by giving you a summary and some takeaways and a quick demo of the exploitation on Chrome and Microsoft Edge. So let's start by taking a look at what a typical V8 exploitation targeting Google Chrome without the V8 Sandbox is looking like. So first, you will need a V8 vulnerability that will lead to memory corruption. That memory corruption, you will need to transform it into some arbitrary read-write that will give you render code execution. From there, you still need to find a Chrome Sandbox bypass or a vulnerability in the kernel in order to get some code execution outside of Chrome. Now with the V8 Sandbox on, so you still need to get the V8 vulnerability that will lead you to have some arbitrary read-write primitives, but that primitives will actually be inside the V8 Sandbox. So here you need a V8 Sandbox escape to get exploit primitives outside of it and get render code execution. Finally, you still need to go through the Chrome Sandbox bypass or the OS kernel vulnerability in order to get code outside of Chrome Sandbox. A quick word about the V8 Sandbox. We'll talk in more details about it later during that talk, but before the V8 Sandbox beta release, which was in March of this year, all the publicly available techniques that were used to escape the sandbox were using row pointers that were stored inside the sandbox. But since the beta release, all the pointers were removed from the sandbox. So for Pwn2Own win, we needed to find a new way to actually escape it. So through that talk, we're going to go through all those steps here, and that's those steps that gave us the win at Pwn2Own. Let's begin by talking about the vulnerability. And first, we'll go through some of the basics that are required to understand properly what's the vulnerability about. So let's create an object, one, with 5 properties, A, B, C, D, and E, and values 1, 2, 3, 4, 5. In memory, the object will look like that. As you can see, there are the values 1, 2, 3, 4, and those are actually the property values stored inside the object, so they are the in-object property values. The rest of the properties will be stored inside a property store outside of the object. Another very crucial field here in the object is its map. It's basically defining the shape or the type of the object, and some interesting fields can be also found here, like the number of descriptors, which is giving information about the number of properties the object has, and the descriptor array. The descriptor array is a structure in memory that is giving information about the properties themselves, like their keys, the index for where the properties are actually stored inside the object or in the property store, and the type of the properties. Like, for example, all of them here are SMIs, which stands for small integers. Now we'll go through some creation of objects in JavaScript in order to understand better what's the concept of descriptor array and transitions. So let's say we have an object 1 here, and let's add property A to it. This will trigger the creation of a new map that will transition from map 0 via the A property, and it will also trigger the creation of a new descriptor array in order to give information about the properties A. Now let's create an object 2 with A and B properties. This will create a new map for that object. And that map will transition from map 1 via the B property. And the new descriptor array giving information about A and B properties will be created. Now, because object 1 and object 2 share the property A, the object 1 will also now use that descriptor array, that new descriptor array, in order to save space in memory. Same thing here, if we create a third object, a new descriptor array will be allocated with A, B, and C properties. And because object 1 and object 2 are sharing some of the properties of object 3, they will use the same descriptor array. So that's it for the descriptor array and transitions. Now we'll talk about foreign loops and enum cache. So when you do a foreign loop like that in JavaScript, it will actually create a structure in memory, which is called an enum cache. That structure is made to filter out enumerable properties from non-enumerable properties in order to make the for loop faster. And because the cache was initialized with object 2, which has 2 properties, then the indices array and keys array inside the enum cache will have a size of 2. Now, inside that foreign loop, the property values will be actually accessed via the gatekey property bytecode, which is handled by the built-in function gatekey property handler. Now let's see what is actually happening if we optimize the foreign loop. So let's put that foreign loop into a function test, and let's optimize it using those built-in function here. What will happen is that the C of nodes that is representing the JavaScript code that you can see on the left here will actually be reduced by the JIT compiler called turbofan in order to optimize those nodes. And one particular node that will be optimized is the JSLoad property that will be optimized by the turbofan in a node called load field by index. So now the properties will now be loaded by index via the enum cache. That leads us to the CV 2023-4427, which was discovered by Sergey Glazunov of Google Project Zero. And we're going to talk about that CV and more precisely about its POC, because the vulnerability we use as Pwn2Own is actually a variant of it. We actually bypassed the patch made for that vulnerability. You can see, OK. So the POC of the CV looks like that. And as you can see here, like most of the code here was already covered during the basics. The only change here is that the trigger function will have a parameter that will be called inside the foreign loop. Another thing to remember here is that at the time of the trigger call here, that trigger function will be optimized by the JIT compiler, which will eventually produce some optimized code and load the property values by index inside a foreign loop. Now we'll go through through the execution of some of the most important lines in the POC in order to understand properly what's the vulnerability about. So on the left, you have the object2 layout in memory, and we'll follow like how the layout is actually evolving. So let's call the callback function in the foreign loop. This will call the callback, and the first line here will change the property C of object3 from a small integer to a double. And this will trigger a map update for the object3. That map update will actually change the map of object3 and the descriptor array of object3. And by transition tree, map2 will also be updated as map2 was linked to the map of object3. So now map2 is linked to descriptor array 4, which is describing C as a double. Next, we'll execute the foreign loop in the object1, which will trigger the initialization of the enum cache based on that object. And because object1 has one property, then the enum cache, and more precisely the keys and indices array inside enum cache, will have a size of 1. Now we'll access actually the property values. We're going to do that by accessing the enum cache and getting the indices array. Then we're going to use the iteration count, which is 0 now because that's the first iteration of the loop, and use it in order to query the indices array. So we get that index from the indices array and use it as an offset from the object2 here in order to get the property value, which is 1 right now. So we've done the first iteration. Let's go through the second iteration. Here we're going to do the same. Call the callback function, but nothing will happen because the object3 was already updated. Now we'll access the property value. And for that, we're going to get the iteration count, which is now 1. And that's where we'll actually access out of bound of the indices array. And that's where the vulnerability lies. From there, we're going to use that out of bound value as an offset from object 2. And this will lead to memory corruption. Now, for the patch of that vulnerability, it actually happens when we update the map of object 3, where a new check is added that is checking if the object 3 old descriptor had an enum cache, or if the new map of the object 3 has some enumerable properties. This was the case, so we're going to actually go into that if statement and initialize a new cache, but based on the object 3 this time. So the size of the indices array would be 3, which will avoid the out of bound from happening. Now the bypass, and that's actually the vulnerability we use at Pwn2Own. It is the POCs on the left, and the POC found by researcher Sergei Glasunov is on the right. And as you can see, they are pretty similar. And in fact, the only difference here is that we added an object with A, B, and G properties. And we're going to see how this addition of that object will actually bypass the patch. So the POC will look like that, and we're going to see in memory what's going on. So object 4 is created with its map, and it will trigger also the creation of a new descriptor array for A, B, and G properties. Now object 1 and object 2 are created, and as you can also notice in map 2 of the object 2, it has a transition array, meaning that we'll have multiple transitions, and one of the transitions is to the map 4 via the G property. Now the object 3 is created, and map 2 has another transition to map 3 via the C property. Now object 3 will also create its own descriptor array to give information about A, B, and C properties. We'll continue by triggering the creation of an enum cache for object 2 using the for in loop. But this enum cache will be created inside for the descriptor array 4. Now we'll execute the map update of the object 3. And we're going to go through the check of the patch. So we're going to take a look at the check here that is checking that the old descriptor, which is on the right here, the old descriptor of the object 3 has an enum cache, but it doesn't have one, right? It's the descriptor array 4 that has one. So we're going to actually bypass it, and then the map and the descriptor array of object 3 will be updated to map 5 and descriptor array 5, which is giving information about the C property as a double. So now, by transition tree, and because map 2 was linked to the map 3 and map 1 is linked to map 2, basically those two maps will also be updated and will point back to the new descriptor array, the one for object 3. And you might recognize actually the same layout as the vulnerability found by Sergei Glasunov. From there, we just need to trigger the creation of a new enum cache of size 1. And we can trigger the same bug as before by accessing out of bound of the indices array and using that out of bound value as an offset from the object to get memory corruption. I will now let Tao talk about the exploitation part.
Good morning, everyone. My name is Tao Yan. Let me introduce the exploitation part of our V8 exploit chain. The first step of the exploitation is triggering JIT stably in Chrome. We use native syntax to trigger JIT before. In the real world, native syntax is not supported. Usually, people use a big number of loops to make the code hard to trigger JIT. So please check the code on the right and the left side. Both of them, you can see, have the same loop count. Guess which one performed better? Please raise your hand if you think the left one performed better. Come on, just guess. You have 50% to answer right. Yeah, one. Please raise your hand if you think the right one performed better. Wow. Yeah. Yeah. If you choose the code on the right side, you will be a browser expert. Believe me. Actually, the turbofan JIT compiler has heuristics for inlining functions and optimizing code. It relies on many factors such as optimizing thresholds, call frequencies, runtime profile, etc. The code density is one of the most important factors. We have known it is indices array out-of-bounds read vulnerability. To exploit, firstly, we need to control the value of the out-of-bounds read. To do that, we set up the number of object items to 1, 9, 10, 11 for the object 1, 2, 3, 4. So the indices array size is 1, and there are 9 items in object 2, so we can control the out-of-bounds read index. Then we allocating a string right after the indices array and the enum cache in the memory in the callback function. By computing the offset of the out-of-bounds read, the controlled string value is located at the indices 7. So we can see the key of the object 2 equals P7 here. And finally, we can read out of any controllable offset of the object 2. After knowing the high-level idea, let's see some more details. Now, iterations number is 7, and here, for in loop is called, and enum cache and indices array are created, and the controllable string is allocated right after the indices array in the memory. Now, the object 2 key will get property value via indices array. Here, out-of-bounds read happens, and the controlled value is retrieved as the offset. Finally, we can control the arbitrary offset of the object 2 for out-of-bounds read. Now we can read arbitrary address of the object 2 in the assembly level. To get a fake object primitive in the JavaScript level, we still need to write the fake object address at a relative address of the object 2 and write the arbitrary value at the fake object address to fake any useful object we want. Let's see how we make it without any help of other vulnerabilities. First, write the arbitrary value at a fixed address. We can create a large array and use a large array element to write the arbitrary value to the large array element address. And it is the address is fixed per resize and a Chrome version. Second, writing the arbitrary value at a relative address of an object. Usually, adjacent objects are good candidates for that purpose, but it doesn't work due to some limitations. So we play with large array element since its address is fixed, and we can easily spray the arbitrary value in its buffer. In the meantime, the object 2 address is allocating a known memory scope. Here is around the hex 15000 in the specific Chrome version. So we can calculate the fixed offset with this equation, the middle address of the large array element minus object 2 address. Although the object 2 address is not fixed, since we spray almost 32 megabytes fake object address in the large array element, so we have a safe sliding zone for object 2. The size of safe sliding zone is also 32 megabytes, which is huge memory scope to ensure the object 2 is allocating the safe sliding zone. Now we succeed to write the arbitrary value at the relative address of the object 2. Then let's see how we fake the object by using features of the V8 heap allocation and manipulating the V8 heap with a large array element. The left side is the theory we mentioned before. The right side is our practice. You can see the object 2 address plus the computed offset will point to the fake object address spray area. And finally, we can use a large array element to create a fake object. In JavaScript level, there are two objects, large array and a fake object, both pointing to the same memory region, causing a useful type confusion scenario. The last step for faking the object is writing the fake object fields with a large array element. To do that, we need to know the map values of the object to be faked. Here are two useful type of arrays to be faked to create more powerful exploit primitives, double array and mixed array. And most importantly, their map values are also fixed per conversion. Here are more details. Since we know the fixed map values of the object to be faked, we use a large array to write the fake object map, element address, length, etc. to the corresponding offset. Finally, we succeed to fake a JS array in JavaScript level, as shown here. Then we'll go through more details about how to create arbitrary read, write, and address of primitive from fake object primitive. Now, the idea is based on both fake object and a large array element pointing to the same memory region. So we use large array to create fake object and use fake object to do read and write. For arbitrary read primitive, we fake double array map and fill arbitrary address which we want to read at the offset of the double array element address field. Then we can call fake 0 to read arbitrary double value inside the V8 sandbox, as shown here. Same case for the arbitrary write primitive. We also fake the same double array and fill the same arbitrary address with arbitrary read. Then we use fake 0 to write int 64 and int 32 value to the arbitrary address inside the V8 sandbox. For address of primitive, we fake the mix array with a packed element map and also create a fake object element right after the fake mix array. When putting an object to the fake 0 in the JavaScript code, the object address will be written to the 0 offset of the fake mix array element data, which is also large array 3. So we can use a large array 3 to read the address of any object. Now we finish our exploit primitives creation, but if we recall the whole process, we may have a question. Are the fixed values really fixed in all situations? We can see all fixed values we use are large array element address and 2 map values. Finally, 2 map values depends on free trunk base and a fixed offset per conversion. Large array element address is sometimes occasionally swing to another address, and when minor MS is turned on, there are some also differences. Let's see how we solve these corner cases to create a close to 100% successful read exploit. For 3 possible large array element addresses, the main idea is we use a large array to create multiple fake objects evenly distributed in a memory region. Here we create 5 fake objects with a gap size, the hex 40000. Then we set in anchor fake object at the address of the hex 140 to 141. After that, we only need to find which fake object is the anchor fake object in different possible addresses. Here we can see the anchor fake object is first, second, and the last, which is 5th fake object respectively. With that, we can calculate which large array pointing to the anchor fake object accordingly in different possible large array element addresses. To find the right index of the large array element pointing to the fake object, we write the fake object 0 with a floating number 1.1, then large array element value will be changed accordingly. So we just need to search which large array element has the changed value. That is the right large array element pointing to the fake object. Last, the scavenger versus minor MS. Scavenger is the V8 current default young generation garbage collector, while minor mark and sweep is the new V8 young generation garbage collector, which is still in development and is experimental feature. You can see free trunk base address depends on the V8 garbage collector, which is fixed. And the difference, you can see the difference about how free trunk base is allocated from the free region list by linear allocator in both garbage collectors. Garbage collector is a big topic, and we don't have time to cover more today. And I leave some homework for you if you are interested.
Awesome. Thanks, Tao. So now we'll talk about the V8 Sandbox and how actually we escaped it to get render code execution. So the goal of the sandbox is basically to get rid of all the row pointers that are used to reference one object to another inside the V8 heap. So the V8 security team, they remove those pointers and replace them by offsets from the sandbox base address. So even if the attacker actually compromised that offset, he won't be able to get outside of the V8 heap. Now to reference objects that are outside of the heap, like the sandbox, the security team also removed those row pointers to replace them by index to pointer tables that are pointing back to the object they want to reference. So there are pointer tables for external objects, like for example for blink objects, for trusted objects like code metadata, bytecode, and for executable objects like GIT code. Now we'll go through some of the WebAssembly internals that are required to understand properly what's the sandbox escape about. So we'll start first by something simple and just creating a module and an instance, WebAssembly module, an instance inside the JavaScript. This will actually allocate RWX memory region in the address space of the process. And when you actually call export function from JavaScript, it will jump to what is called a call target here. And that call target is actually landing in a structure named main.gem table, which has the purpose of jumping directly to the compiled code of the function that is being executed. There is also a far.gem table, but we won't talk about it as it's not very useful to the understanding of the escape. Now we'll go through some of the structure inside memory, so instance and modules first. So when you create a module from JavaScript, it will create a WebAssembly instance object that has an index to a trusted pointer table, which is pointing to a trusted instance data, where there are important fields like WebAssembly dispatch table and gem table start, and we'll see later how we use them to actually escape the sandbox. Then that instance object is also linked to a module object, which has index to an external pointer table, pointing to a native module, and that native module pointing back to a WebAssembly module. Now, a very crucial field in the WebAssembly module is the vector of WebAssembly function, because we're going to use that also for the sandbox escape part. Now, when you actually get a reference to an export function, a WebAssembly export function, it will create in memory that structure here, and that will lead to its function data. Now, in its function data, there are also interesting information like the index of the export function, the instance the function is actually linked to, and the internal representation of the function, which is pointing back to the external one. Now we'll introduce the concept of WebAssembly table and indirect call. So let's first create a module. Let's name it module 0. And that module is declaring a function called indirect. And it's just returning a simple float here, 0.015 here. And then we're going to actually reference that function inside the JavaScript, so we can use it later in JavaScript. We'll create now a new module. Let's name it module 1. And we're going to create a WebAssembly table and import that table at the time of instantiation of the module. And I'm going to reference that WebAssembly table also inside the module directly. Now what we're going to do is we're going to take the reference to the indirect function, which is from the module 0, and set it at index 0 of the WebAssembly table. So when we call the main function here, what will happen is that the module 1 will call indirectly the indirect function, which is from module 0. And we will do that by querying like the WebAssembly table at index 0. Here, the result is just multiplying the return address of the indirect call by the parameter, which is 1,000 here. So we'll give 15 as a result. Now, internally, what's going on when we actually set the indirect function at index 0 of the WebAssembly table, it will call the internal API set function table entry, where we will first get the function index of the export function passed as a parameter via the structure parsing that you can see on the left. Then we're going to query the vector of WebAssembly function from the module of the instance that the export function is linked to in order to get the static representation of that function inside the C++ code. and use that function as a parameter inside the update dispatch table, where we're going to use that function, and more specifically its function index, inside as a parameter for the get call target call here, which is computed the call target of the function, and use that in order to set the call target inside the dispatch table. As can be seen on the left here, the dispatch table has now index 0, the call target of the indirect function. Maybe a bit more precision about how the call target is actually computed. It is based on the jump table start, which is the address of the base address of the main jump table, plus an offset, which is computed based on that equation. You don't need to remember the equation, just that the equation is based on the function index. So when we go back to JavaScript, we set the function, so the call target of the indirect function will be set inside the dispatch table. And when we call the main function, which is from instance 1, it will access that dispatch table at index 0 to get the call target of the indirect function to jump to the instance 0 memory allocated for that instance, and execute the code of the indirect function. Now, if you followed along, you might have noticed that if we control the function index here, we are actually controlling the call target. And if we control the call target, we can pretty much jump everywhere inside the instance RWX memory, which gives us a control flow hijacking primitive. So that leads us to talk about the actual escape. For the escape, we have a setup to do. First, we need to create 3 modules. So the first module is just declaring a function that will be called indirectly. Doesn't really matter what it does. Module 1 is actually importing a WebAssembly table and calling indirectly the function that is from the module 0. A part of that doesn't really matter what it does. And the last module, module 2, is defining a large number of functions. And it does that because the last function, which will have an index n, that index n which will be actually used to compute the call target. So it needs to be actually pretty large. So now step 2 is actually to confuse some fields inside the sandbox. And the first field we're going to confuse is the WebAssembly module object. So now we're going to put, using our arbitrary read-write primitives, we're going to put the module object 2 inside the module object, inside the instance object 0, sorry. So it would look like that. And the other field that we're going to confuse is the index of the export function. So in its function data here, we're going to replace its index, which was 0, by n here, which is the index of the last function inside the module 2. When we do that, actually the memory will look like that. So you can see the function data of the indirect export function, which is the index n, which has the index n now, and the instance 0 is now pointing to the object 2 instead of module object 0. So if we go back to JavaScript, and we set the function, it will call the set function table entry, get the function index, and now it will be n instead of 0. And here we're going to use the instance data of the instance 0 to get its module, which will be now module 2 instead of module 0, to get actually the static representation of the last function of the module 2 here. Using the n index. And this is used to actually avoid a potential out-of-bound error, but it doesn't really matter. The only thing that matters is that the function that is queried here and that the function index is n. Then we use that function here as before to compute the call target. And this is actually the confused WebAssembly function from module 2, not the function from module 0 here. So its index will be n. And we use that n index to compute the call target. So if we come back to JavaScript, here we are setting the indirect function at index 0, but now indirect function has index n, right? So when we compute its call target, it will be equal to jump table start plus n, or like something based on n. But for simplicity reason, we just put n here. So when we call the exploit function and access that dispatch table to get the call target, in order to jump to the instance 0, we'll actually jump out of bound of the main jump table, and we can pretty much jump everywhere inside that RWX memory. which give us the control flow hijacking primitive. Now to go from that primitive to code execution, we still have some stuff to do because we don't have any arbitrary write, so we can't write shellcode directly there. So we use a trick, which is that in WebAssembly, floating points are compiled as 64-bit values by the WebAssembly baseline compiler, which is liftoff. And so this is pretty cool because using that, we can just encode our shellcode as 64 as floating points, and they will be compiled in RWX memory as 64-bit pointers. From there, we can use our control flow hijacking primitive to jump to the start of the first floating points in memory, which will be the first 64-bit value, and it will be the start of our shellcode. Yeah. So now we'll let Tao finish the talk.
Yeah, we have talked a lot. Let's wrapping everything up right now. Firstly, we have an out-of-bounds read vulnerability, and we converted to the fake object primitive, and further to more powerful exploit primitives with some advanced exploitation techniques. And then we use a new field confusion technique to hijack a WebAssembly core target address to escape V8 Sandbox. And last, our exploit is robust and stable enough to work on both Chrome and Edge, although there are some difference between them, such as versions, the object2 addresses, etc. Now it's demo time. We'll do a live demo. And let's see. Yeah, perfect. You can see the Chrome version here is M123. It is the latest version at the Pwn2Own 2024 or Vancouver. And we close. Okay.
Yeah.
Wow. Okay, we close. Yeah, this is Microsoft Edge. You can see the version is M122. The update is a little bit later than Chrome, but it doesn't matter. Our exploit is robust and stable enough to fit all of them. Close. Then we clean the environment. Make the environment clean. All right. Let's execute our exploit on Chrome first. Let's go. Okay, you can see the notepad pop out, very stable and fast. Then Microsoft Edge. Then let's go. Cool. You can see the also very stable and fast. Now the last slide, the summary and the takeaways. The first, history doesn't repeat itself, but it rhymes. Humans repeatedly make similar mistakes, but how to effectively and efficiently discover them were small explorations. Second, the exploitation ideas and techniques used in our V8 exploit chain are universal and can be used in other similar vulnerability exploitations. And also, if you want to make your exploit to be an art, one of the best ways is to exploring and filling the big gap between a working exploit and a close to 100% successful read exploit. Third, sandboxed object fields such as index, offsets, internal pointers are the design of the V8 Sandbox. It is really hard to patch this kind of field confusion techniques. So we believe our new field confusion technique would lead the way to a new V8 Sandbox escape era. The last but not the least, think about defense like an exploiter. It's really, really important. Thanks to everyone. I think we are on time. Yeah.
Good job.